Okay, so let's now go back to looking at relation classes and how that ties to congruences. So let's recall that a relation class, these are all of the elements related to a given element. So when we looked at some examples in the past of, let's say, for instance, we were looking at the relation of A is less than B, then all of the elements related to A were all of those that were larger than B. So we had that interval of everything larger than it. So we looked at relation classes, so we'd like to understand that now in regards to congruences. So for congruences, it is all the numbers that are congruent to a given number, and this is going to be for a fixed n. So technically the relation is really congruence modulo n, so the n really needs to be fixed when you're talking about this relation. But in general, I mean, just for intuition, we're really just talking about congruences still. But indeed, we have this for a fixed n. So if we take a look at an example, let's say n is equal to 3. So we're going to try to study all of these relation classes modulo 3. So if we think about a relation class of 0, so we're thinking, okay, what are all of the numbers that are related to 0? Okay, so we think about 0. What is 0 equivalent to modulo 3? Well, we know within the set there has to be the number 0, right? Because we showed last time that this relation is reflexive. So we showed that 0 is then related to 0. In other words, 0 is congruent to 0 because anything is related to itself. So mod 3, indeed, this is true. So 0 is inside this list of numbers. Then if we're trying to think about the intuition of, we're looking at numbers that have the same remainder when we divide by 3 that 0 does. So if we take 0, we divide it by 3, our remainder is 0. So what other numbers when we divide it by 3 do we have a remainder of 0? Well, obviously we have 3. Right, 3. So you could prove this if you want to. You say 3, we could try to show that 0 is congruent to 3 mod 3. And what we're doing is we're saying 0 times 3, that's equal to negative 3, but that's negative 1 times 3. So we showed the existence of an integer that makes this true. So by definition, these two are equivalent. By same idea, we could also say negative 3 is also true, right? Because we're looking at any integer, not just positive ones. We could also say 6, and 9, and 12, and so on and so forth. And in this direction, we also have negative 6, and so on and so forth. So we have all of these multiples of 3. That defines our relation class of 0. Okay, if we move on then to the relation class of 1. Obviously, since this relation is reflexive, we have 1 appears there. Now we're trying to come up with all of the other numbers that have the same remainder when we divide it by 3. So 1 divided by 3 gives us a remainder of 1. So the other ones that have a remainder of 1 are going to be 4, and 7, and 10, and 13, and so on and so forth. And in this direction, it would be negative 2, negative 5, and so on and so forth. So all of these, if you divide it by 3, you get a remainder of negative 1. Now if we take, a remainder of positive 1. My bad. So we have the relation class now of 2. Well, we know obviously 2 is going to be in this list. And then if we think about all the other numbers that have the same property as 2, well then that would be 5, and that would be 8, and that would be 11, and so on and so forth. And then if we go in the other direction, we'd have negative 1, we'd have negative 4, and so on and so forth. So notice real quick here that when we look at these congruences, these congruent classes, or these, in this case, we're talking about relation classes, but these are really congruence classes, all of these numbers, hopefully we recognize a pattern, right? We're just simply adding 3 to get more and more numbers on this list. We just happen to be starting with 0, and then adding and subtracting 3. Here we start with 1, add and subtract 3. Here we start with 2 and add and subtract 3, and we get all of these lists. So, okay, that's 3 of ours. Let's say what happens if we go to 3. We'd like to understand what is the relation class for 3. Well, then obviously we know 3 is going to be in this list. And then just the same pattern that we recognize, we can add and subtract 3. So we'll have 6, 9, 12, 15, so on and so forth. We subtract 3, we get 0, we get -3, we get -6, and so on and so forth. So this is now my relation class for 3. You can repeat this, look at the relation class for 4, but hopefully, if you take a look at this, you notice something unique about this relation class of 3. This relation class is the same as this relation class, right? These two sets are identical because they have the same elements. So what we now see is that the relation class of 0 is the same as the relation class of 3. Then if you had to think about it, then what about 1? Well, then probably that would be the same thing as 4, right? Because we see that 4 appears on this list. So if we started for the relation class of 4, we would add and subtract 3's, and we would get the same thing. So this would be the same as the relation class of 4. The relation class of 2 is the same as the relation class of 5. But that's not it, right? We could make a huge list of all of these relation classes, because obviously the relation class of 0 is the same as the relation class of 3 because they form the same set. That also seems to be the same case. The relation class of 6, you'd have 6 in that, and then you'd add and subtract copies of 3, and you would get the same exact set. So this is the same as the relation class of 6, which is the same as the relation class of 9, and so on. And this would be the same as the relation class of 7, which is the same as the relation class of 10, and so on and so forth. And this is the same as the relation class of 8, which is the same as the relation class of 11, and so on and so forth. So what we now see is that all of our relation classes are going to fall within these 3 categories, right? Either, if I give you any integer, the relation class is going to be the same as the relation class of 0, the relation class of 1, or the relation class of 2. So we see the integers modulo 3 have 3 distinct relation classes. And these 3 distinct relation classes, I'm just going to call these 0, 1, and 2. So you could have chosen any other list, right? You could have said the relation classes are 0, 4, and 11, right? Those also still describe all of these. But just for clarity, I'm just going to choose these smallest non-negative ones and list these off. Now, remember, these are sets. These are still the same thing that we've been studying for a while. They're just groups of elements. What do we notice then if we were to have all of these put together? So if we were to look at the relation class of 0, union the relation class of 1, union the relation class of 2, what do we see? Well, if we take all of these numbers here, all of these numbers and all of these numbers, so if we look at these first 3 sets, we take the union, so we include all of them. Well, we have 0, 1, 2, 3, 4, 5, 6, 7, 8, and we go in the negative direction, -1, -2, -3, -4, -5, -6. All of the integers are present. So we have this fact that when we put all of these 3 together, we get the integers. Also, as something that's neat here is that if we look at this set intersected, the set containing 1, we say how many things are in both of these sets? Well, there's nothing, right? There's nothing in common. So this is the empty set. If we take a look at this intersect the relation class of 2, well, what do these have in common? Again, there's nothing. And then we have the relation class of 1 intersect the relation class of 2. Well, again, there's nothing in common. So what you have is you have the integers, and we essentially have divided the integers into these 3 distinct groups where there's no overlap between any of these groups, but you put them all together and you get all of the integers. But that's at least true for integers modulo 3. What about for other cases? Well, we'll come back to that and see how do we see some of these relations, how can we prove some of these to be true for a general n.